This is some work that developed out of efforts to extend the ideas of sequence covering arrays from individual events to combinations of parameter values. And it looks like it might be pretty useful, and a really interesting aspect of this work is that it turned out that the problem was easier to solve in the end than it appeared at first, and we'll get into that later. And we have an example of where this could be used. This is in particular useful for state-based systems, but of course many or probably most systems have some states that are essential, but there are other systems that are very strongly state-based, such as protocols, communication protocols, and the like. And so this work could be especially useful in those cases. So why would we need to look at the order of input combinations? Well, of course, that's pretty obvious. Covering arrays are very useful, clearly, but of course the sequence of inputs, and the inputs meaning combinations of parameter values, those inputs can make a big difference when state is maintained by the system. And of course, sequence covering arrays look at sequences of events. A lot of people in this workshop have looked at sequence covering arrays, and they can be very useful for many applications, but they are, again, strictly individual events, the order of individual events, and we'll get into that in a little while also. And the states of a system, of course, change according to inputs, and the combination of input values can matter a lot. If there's a branching condition that includes 2, 3, some number of input values, then of course the whether that state changes according to that branch condition depends on the inputs that are seen by the program. And so obviously we do want to consider the order of inputs of combinations in a test set. Let's first talk about what we mean by ordered combinations and distinguish these from sequence covering. Sequence covering arrays have been around for a while, of course, and an example of those, that's on the left, where we have A, B, C, and D are individual events, and each row represents one test sequence. So the sequence covering array would have all sequences of events for some specified length, 2, 3, or so on, and the events are separate and non-repeating. Now, on the right-hand side, we have an example of what we're talking about with this new work, which is ordered combinations. And in this case, what we're looking at are combinations of parameter values. So it's a little bit different orientation. Again, back to the left-hand side, we have sequences of events represented by rows, but each event occurs in one column of the row, whereas on the right-hand side with the ordered combinations, we're looking at it from a different standpoint. Typical test input sequence, and the orders that we are concerned about are the orders of test values as they are entered into the system. So what the sequence, or what the combination order looks at in this case, are cases where a particular combination of values is eventually followed by some other combination of values. And of course these numbers get very large, which we'll talk about. But an example would be in test 1, we have P0 and P1 are equal to A and D. And in test 6, we have P2 and P3 are equal to C and B. So P0, P1 equals AD is eventually followed by P2, P3 equals CB. This is just a simple example to illustrate what we're referring to, and in this case, just to show that the order of inputs, of course, affects error detection. And in this example, we have an error condition that's reached when P1 and P2 is followed by P1 and not P2. But that order is not necessarily going to happen depending on the order in which tests are entered. So if we enter tests in the order shown in the matrix in the center, then of course we have the second condition shown in blue occurs before the first condition, which is shown in yellow. But if we reorder the tests as shown below that, 1, 2, 4, 3, 5, 6, then that problem is solved and the error condition will be exposed. So nothing surprising, but just to illustrate what we mean here. Just to define a little more formally what we're referring to, what we have are orders of T-way combinations. Of course, T-way combinations are as what you would have in any covering array, and we're looking at orders of length S. So what that means, of course, is that a particular combination is eventually followed by the other combinations in the order. For example, the one that we gave earlier, where P0, P1 equals AD is eventually followed by P2, P3 equals CB. And of course, looking at that matrix at the lower right hand corner, you can see that there are obviously many, many different ways that these orders can occur. The expression in the center gives the number of these. Obviously, it gets very large, so it looks like it might be somewhat complex to find these orders and cover all of the eventually following S-length orders of input parameter values. So that is the problem that we've set out to solve, and actually it turns out to be a little easier than we might have thought. So this is a nice little result that we can cover all S orders of T-way combinations if and only if we have a series containing a total of S covering arrays, each one of strength T, of course. So what we can do is obviously make a T-way covering array and then duplicate it S number of times. So that is a quick and efficient way to do this. We know how to generate practical sized covering arrays in a reasonable amount of time for most test problems. So we simply duplicate that and have a much stronger test suite, we believe. We hope it'll be stronger. That'll be future work to try this out on some empirical examples. So a question that naturally arises is what happens when we change that constraint where a combination is eventually followed by another combination or multiple combinations to the case where the combination is immediately followed by another combination. So that means, of course, that the input combinations occur in consecutive rows. So that means no interleaving between the ordered combinations that in this case, the examples C1 eventually followed by 2, C2, that's what we referred to earlier as the ordered combination coverage. But adjacent ordering is, again, where it's immediately followed by another combination. And so that means that they are in consecutive rows, and we need to be able to produce an ordering of combinations. What this amounts to is that every T-length permutation of combinations occurs as a set of test rows in some sequential inputs so that they occur as the tests are executed in every permutation for the combinations of values. Now, if you're familiar with what's called a De Bruijn sequence, that is where we do have a sequence of characters, symbols, where every T-length permutation occurs. So this naturally looks like it might apply nicely to this problem of adjacent combination covering, and so that's what we can do to produce the ordering that we want. De Bruyn sequences are an interesting concept developed in the late 19th century, early 20th century, and a lot of properties were proved by the mathematician De Bruyn. Basically, fairly simple to define. For some set of k symbols, we want to include every n-length permutation of those symbols. And the length of this sequence is k to the n, and it's been shown that there is no way to do a shorter sequence covering all those n-length permutations. And of course, just to show what we mean by these, there's a fun little example. As noted, probably many thousands of hackers have reinvented this idea without even knowing what it was called, because it has a natural application in cracking key code locks. A little example at the lower right-hand side there, a car door lock. I actually had a car like this where it's got 5 keys, and you input a sequence of 4 or maybe 5 digits, or four key presses actually, to unlock the car. And there is no enter key, so if you just keep pressing keys, eventually you may reach the combination that the car is looking for. And if you use a De Bruyn sequence, you can do this very quickly. If we had a length 2 sequence at the lower left side of the slide, of course, if we had a combination of 1, 0, then the inefficient, naive way to do this would be enter 0, 0, then 0, 1, then 0, 2, and then 1, 0. But if you use the De Bruyn sequence shown at the very bottom on the left, 0, 0, 1, 0, and then the car door opens. So only 4 key presses instead of 8, or possibly if there was an enter key, then even more. So what this means as a practical example is that it's easy to break into a car in a few minutes because of the efficiency of using the De Bruyn sequence. To use the De Bruyn sequence for generating ordered combination covers, we'll start out by simply producing a covering array of the desired strength T-way coverage for the system that we want to test. Then number the rows of the covering array, so 1 to k. So let's say we have k rows in the covering array, and we want to cover s-length sequences. So just generate a De Bruyn sequence of ks for the k row indices. And as a result, what we can do then is write down the row numbers, and then we're going to fill the rows in from the covering array. And the number of test rows that we end up with for the adjacent ordered combination cover is that expression shown at the bottom. And I do want to thank one of the reviewers for pointing out that we added that little s-1. We had neglected that. The circularity of the De Bruyn sequence results in that s-1 addition of rows that we want to append the first s-1 rows to the final test array. Here's an example just to show how this works. So let's say we have a covering array as shown here with 6 rows. So we have row numbers 1 to 6. And we'll do a De Bruyn sequence using those digits. And we come out with the sequence shown on the bottom. And then we can simply list those vertically and start replacing the digits with the rows that they correspond to. So very simple process, results in an efficient result, and very useful. To illustrate how this might be used in practice, we're going to turn to a very old example, but very well known if you're concerned with software testing, software safety. This is the Therac 25 example where there was a radiation therapy machine, and it killed several people between 1985 and 1987. It had a number of different bugs in the software, but in particular there was a race condition where an error occurred if the human operator was moving a little too fast on the keyboard, and if they first selected an X-ray beam and then switched to an electron beam, the machine could do both X-rays and electron beams. And if there wasn't enough time between the selections, then it ended up sending X-rays instead. And of course, ionizing radiation for high power for long periods of time was very dangerous and fatal in a number of cases. Just to show how we could develop a test set that could detect this error where it might not be detected using random tests or expert design tests and so on. But if we use this adjacent covering of combination orders, then we could detect it. So let's say we have 4 parameters, P1 through 4, where P1 is the minimum time between option selections. So there's a certain amount of time that was required. Of course, if you remember the previous slide, very old machine involved, so minimum amount of time. P2 represents the X-ray beam, either selected or not selected. Likewise for the third parameter, whether the electron beam is selected or not selected. And then a fourth parameter that is used to indicate the start of whichever beam was selected. And what happens then is that the error would occur if the sequence shown there, P1 through 4, is equal to 1, 1, 0, 0. That selects the X-ray beam, and if that is immediately then followed by P1 through 4 equals 0, 0, 1, 1, where there was not sufficient time for the X-ray, but the electron beam was selected and the beam was started. So what happened in that case is that the operator thought that the electron beam was engaged and started that, when it was actually the much more high power, dangerous ionizing radiation from the X-ray beam. So we will get this particular sequence in tests generated using the adjacent covering array, adjacent combination covering array, whereas again, we probably wouldn't see this particular sequence, or we might not see it if we generated tests randomly or using some other approach. We also have a sort of simple prototype tool that is used for identifying missing orders. This is just an example where we have, in this case, a test set with 4 variables, 12 different tests. So what we see here highlighted or outlined in red is a particular set of values for A and B, 1, 1, and we can see highlighted and surrounded in green. It is followed by values of C and D of 0, 1, and 1, 0. So the simple little tool will identify that we're missing 2 orders, in this case two sequence of 1, 1 followed by 2, 3 equals 1, 1, or AB equals 1, 1 followed by C and D equals 0, 0. So fairly simple. We would like to improve this and build something a little more user-friendly, but useful so far. We also generate some statistics. This is a really small example, but just to show how this works. So the top half where it says static, that's input space coverage. That's the usual combinatorial coverage. A lot of tools available for that. Just simple combinatorial coverage. What we refer to as dynamic there, this is the combination order coverage. So the columns on the left there, 1 way and 2 sequence and so on, that indicates the values of T. So T of 1 followed by later T of 2, and then the second column there where it says 2 sequence and 3 sequence, that refers to the the value of S for the orders, the 2-order and 3-order sequences. So what we have there at the bottom, two-way combinations, all three sequences of those permutations of 3. So some numbers that we show at the right, and that gives the coverage. Again, we want to improve this tool and make this a lot more useful for practical testing. And where do we want to go with this next? Well, the first order of business would be try it out on real-world problems. There's a lot of possible uses. Network protocols mentioned earlier, which are something that are really important, both security-wise and just from a reliability standpoint. This could be quite effective, we think, for testing network protocols. We could consider automatic test pattern generation for sequential circuits. Digital systems testing is important. And kind of a more current sort of topical example would be smart contracts and blockchain. So a smart contract, if you're familiar with those, the idea is that you've got computer code that is basically unchangeable and is going to be making decisions that might be critical. So that needs to be, of course, very carefully tested. So that might be a case where we could apply this. The other characteristic of the smart contracts is that they thankfully tend to be very small programs, so they might be a good place to start. We'd like to compare this with random testing, standard structural coverage criteria, and so on, and also see if we can possibly integrate this into standard combinatorial testing tools. Build a bigger suite of testing tools could be quite useful. And then a big question is what happens with constraints, always important. So we can look at constraints on sequencing. Of course, since we build the sequences out of covering arrays, then we can use the standard covering array constraints very easily. That's a solved problem. So we're looking strictly, in this case, at constraints on the sequencing. And again, much better tool support would be very helpful. So I hope this has been somewhat interesting and useful. And of course, if there is some interest in it, then please feel free to contact any of us at NIST, and we'd love to talk about it more.